Hello and welcome. I've been planning to do this video for a few months, but I had trouble finding time to record it and then compile it. I had a few problems with my Focus TCM and I realized that there is very limited knowledge and visibility available on internet about the overall fault rectification of the TCM itself. I was able to find a few bits and pieces from YouTube where people are able to crack open the TCM housing, but still very little information was available on how to separate the upper section of the circuit board that is press fitted on top of the lower section of the TCM. Even if someone was able to separate the two halves, the next question was now what? I mean, there is literally none, next to none information available on fault-specific rectification process, on where exactly to look for and what exactly to look for to rectify a specific error code. With this video, I aim to bring you a few technical areas on the TCM which were previously ignored or not explored. Areas like how to separate the top section of the board from the lower section and what kind of effort is involved in it. Secondly, to build a level of familiarity with the TCM board, especially the lower one, and what functions does it serve, and to provide a kind of a map for fault versus probable area which you need to look at if you're battling a specific TCM code. Then I'll also cover some of the hardware that the TCM uses, specifically the MOSFETs and the roles that it play, which you can use this information to order the spares to fix the TCM board. I also spent some time on the TCM to draw up a basic level of TCM interconnection diagram and how it works. I'll take you guys through it, and in the end, I'll show you how to test some of the TCM parts. So for just now, you can just enjoy this video where I spent around 30 minutes battling with the TCM casing and removing the top section of the printed board.
So this is the lower side of the upper side of the upper board. You can see that there is a big chip right in the middle. This is probably a processor of some sort. Uh, on the right and left, these are the pins that came out of this board, and the pins actually belong to the lower board. Uh, Rest of it, there's lots of small resistors and diodes on top of it, but I did not study this board in detail because most of our issues are related to the lower board, so I'll just focus on that one. This is the back side of the upper board. You can see that on some of these places there are some marks here and there. This resulted from me prying it out of its chassis. So if you want to be careful, you can put some cloth to protect it. The only real threat to this particular board is that it can crack. So do not apply unnecessarily excessive force. Just make sure that you know what you're doing. So this is the main board of interest and the board that we'll be focusing on because most of our answers lie in the construction of this board. So if you look at this board, first of all, there is a capacitor that resides over here. Underneath this capacitor, there is an inductor. So, and there is also somewhere in between either a diode or a MOSFET. So it, in the end, it performs as a boost converter. So the so the voltage that this board gets, it magnifies the voltage to around 60 volt for all these MOSFETs to work on. These are power MOSFETs, and they use the uh, uh, upstepped DC voltage from this booster setup to control the actuator motors. So before we move forward, have a look at these three pins. So these three pins on the right and these three pins on the left, they control the motors that control the changing of the gears in the actual gearbox. And there are some MOSFETs all around the board. So before I move forward, you can see that there are some pins that are coming into this board on different parts. So these pins actually directly connect to the connector at the back, that is the TCM connector. And I was able to find this TCM diagram. It's a generic diagram for the same DPS6 transmission for this one that's applicable to the dry DCT one. So you can see that there's clutch motor 1, clutch motor 2, some sensors here and there, and this is the transmission control module on the left and the right. Uh, it's still available on the internet if you want to have a look at it. But the way I utilized it was that uh, I realized that there are 8 pins coming out of both clutch motors. So three of these pins uh, they connect to the phase UVW, and then there are three UVW phase for the second clutch motor, and then there are three of these pins are Hall effect sensors, and then the last two pins are the 5-volt supply voltage and the ground pins. So we'll see in detail how it works. The way it works is that, for example, this is a generic motor diagram where we have three different windings. So assume that these are the UVW windings from the last diagram. Uh, so the TCM has separate supply to UVW windings, and then these UVW windings, when TCM injects power through them, the motor rotates, and when the motor rotates, the Hall sensors, which are positioned at 120 degrees within the motor, they detect the change in the magnetic field, and that is fed back into the TCM, which is then used by the TCM processor to to identify the position of the motor, position of the clutch motor. Uh, this is how it identifies how deep the clutch is traveling to engage and disengage. Um, and primarily, this is how it knows where the clutch essentially is. So if you look at all these DCTs, which are the trouble cores, you will see that most of them are related to the TCM not knowing where the clutch motor is, what's the position of the clutch motor. So, for example, when it says to P2 at 7A means that clutch B is stuck engaged. So the PCM thinks that it is stuck engaged, but it's actually not. It's just that PCM is not receiving any feedback from any significant feedback from Hall sensors to determine that whether it has disengaged or not. So the last feedback that it received was that yeah, it traveled inside, but even though it injected some power into the coils, it should have redirected back, but it did not get any confirmation from the Hall sensors. So all these codes in the end are related to either the power not getting to these windings or PCM not knowing that based on the Hall sensor data that PCM does not know conclusively the position of a clutch motor. So let's get back to the TCM board that we have. I was able to point out that these are pins, the pins of those clutch motors, the UVWs, the UVW phases for both the clutch motors and also the Hall effect sensor. They all were identified some over here. They will all end up over here. The pin to pin contact, I got continuity on all these points. So the first one, the clutch A one, let's check out the clutch A. For example, you remember from one of the drawings that there are 8 connectors to each clutch motor. So here are your 8 connectors: one, two, three, four, five, 6, 7, 8. The one on the right, two of a pair of these pins represent a single pin. This is because these are the clutch A power supply pins, and they needed a larger contact area to deliver effective amount of power due to the limitation on the pin size. So instead of this is one of the good things that they did with this TCM board, because they knew that they were going to use compression fit pins. So they just made sure that there is enough contact area available for the power to be transmitted. And usually we do not have any errors that specifically come out of this, because there is a redundant pin that's already there. But usually the problem that we have mostly originates from here, where we have only one pin. So this is the supply and ground voltage pin, and these three are the clutch A Hall effect sensor circuits, and these are the most common points of failure on these boards. So similarly for clutch B, we have these 3 power pins. So in clutch A, there were these three, and in clutch B, there are these 3 power pins. Similarly, the Hall effect sensor points are over here, 1, 2, 3. So this area in general, if you look at these pins, 1, 2, 3, and this 4, 5, and then 6, 7, 6. So these are the pins if you just want to pinpoint out and just want to fix only a few pins, then these are the pins that you need to concentrate on. The rest of them do not pose enough of trouble. So mostly these error codes that we discussed earlier, all of them originates in this area. So moving forward, I was able to point out some continuities between different points. For example, if you look at clutch B, we'll just take clutch B for example. So the clutch B, especially the power to the MOSFETs, you can see that it connects to all these MOSFETs. So I actually went through most of these context points and tried to draw these lines to find out where each of these MOSFETs connect and how do they work out. So in the end, I realized that for clutch A, the power feed MOSFETs are 6 in total. So these are 1, 2, 3, 4, 5, and 6. Similarly, we have 6 of power B, we have 6 of these MOSFETs for clutch B power feed, and these are 1, 2, 3, 4, 5, 6. Similarly, the 2 motors that move around the gears in the gearbox, we again have 6 power MOSFETs for both of these motors. So for one motor, we have 1, 2, 3, 4, 5, 6. For the other motor, we have 1, 2, 3, 4, 5, and 6 one is under this one, this casing. I also I also noted the actual MOSFET models for these MOSFETs that are being used. So all these buck 765 R2s, they are used for clutch motor A and clutch motor B, and all these QN0406. These are the MOSFET models that these boards are using for the gearbox motors 1 and 2. There are a couple of other MOSFETs. For example, this is the only MOSFET of this name, 2N04H4. This MOSFET is actually part of the power supply circuit, the boost converter. It takes the power from over here, the 12-volt power, it comes to this MOSFET, and then it goes to this boost converter. So if you have generic power failure, then the capacitor, the inductor, or this MOSFET you're looking at. I was unable to figure out what these two do, the Buck 7635-55 MOSFETs. My best bet is that they are providing power supply to the processor that's on the first level, the board that we saw in the initial photographs. So I think that these two supply power to the board above. So this is a very good diagram where it actually describes how these six motors work in tandem to move the motor around in clockwise and anti-clockwise direction, right and left, and using only these six MOSFETs, how this motor works. So let's just look at this diagram where we have these six MOSFETs. We've already seen that all the clutch motors and the gear motors need six of the MOSFETs to work. So let's just say that we have a motor with three windings, U, V, and W, and these are connected to these set of MOSFETs in this aspect. So if let's just say that a microcontroller, which is driving the gates of these MOSFETs, it shuts down. U. Where is U? U is the one in the middle. V is the one on the right, and W is the one on the left. So if U is positive and V is negative, it will mean that this MOSFET will be shut, and also since the V is negative, so this one will be shut. So when these two are shut, what will happen is that current will flow from here, go all the way into the U, come out of this V winding, go through here, which is the V1, and then it goes to the positive of the battery. So similarly, on the next cycle, U is positive, but this time W is negative. So it means that again, U will still be shut. So the gate is closed here, so it has a path to flow into U. But this time, instead of going to V, it will go to W, go to the last N, and from here it will find a way forward into the positive. So because these two are shut now. So similarly, you can look at here and establish that how it's going to work. So all these, there's only three wires that are going to a motor, and on three of these wires will be used for going for pushing the current in and out of the motor. Sometime it will be pushing the current in, sometime it will be pushing the current out. So here it's shown as the Hall effect sensors, but these Hall effect sensors are only available for the clutch motors. For the motors that are going into the gearbox, we have seen that they are not there. It uses a separate mechanism to establish uh, whether the motor has traveled all the way to the end or not. Probably some of you guys might be familiar uh, with a small knob that's present on the casing, on the housing of the gearbox. Sometime if it's broken, then the car is unavailable to engage its reverse because it will not know where to stop. So that is the mechanism that it uses for the main motors. So after that, I'll just go back to the drawing that I made based on the information that I have. I'm just gonna go through this drawing. It's essentially the same drawing repeated for all the four motors. Two of them are clutch motor A, sorry, the motor A and motor B, and the two of them are clutch A and power supply, clutch A power supply and clutch B power supply. Essentially, we again have the same setup. We have six MOSFETs that control one clutch, six MOSFETs that control second clutch, one motor and the second motor. The first section is some sort of a boost converter over here. There's an inductor and a capacitor. This is not the right diagram for a boost converter, but I'm pretty sure I'm missing a few pieces over here. So just ignore it, but do keep in mind that if you're looking at the voltage supply issues, you need to focus on this portion only. If you want to find out if you are looking for any issues that has something to do with clutch A or clutch B, I've already shown you the photos, and you can have a better look at this diagram, and this will give you an idea how the power distribution inside the TCM works, especially for the motors. The Q1 and Q2s that I mentioned down there, the Q1s and Q2s, these are the uh, two MOSFETs that are utilized on these TCMs. In the end, I would just like to discuss the testing methods for both type of MOSFETs that we have. Both of these MOSFETs are almost identical as far as the characteristics are concerned. There was minor differences, especially around the amount of power that both can handle. The Box 765R2 can handle up to 200 watts, while this one, which is QNO406, it can handle up to 100 watts. Operational temperature rating is from neg 75 to 1 neg 55 to 175, and the operating voltage is around 40 volts. So these high power MOSFETs are relatively, you need a breakdown threshold voltage of the gate to source voltage of around about 3 to 4 volts to test it, unlike the regular MOSFETs where you just touch the tip of your multimeter to see if the gate opens or not. So the way I did was I used a 9 volt battery, and I used this setup. And when I touched the plus to gate and the negative to source, at that time the meter leads connected to these two terminals, they would short out, which would indicate that the source to drain switch is working. So I went through all of my MOSFETs on the board and checked every one of them. I did not find any fault with any of those MOSFETs, which actually is another indicative of the problems that we have, the residual problem that the pins that do not get good enough contact with the board itself, and with the temperature changes, they show intermittent working behavior, and sometimes they're non-responsive. So based on this, I'm just going to go ahead and put my boards back together. I'll just solder the points out, to solder the contacts, and yeah, I should see whether it's working or not. Currently, I do not have a car where I can put it in and see whether the fix worked or not. I just have an old TCM, but I'm looking for a project right now, and hopefully I should be able to test it out sooner. Thank you for watching.